Uh, we will next discuss the physical property of the traveling wave on the string. This physical property is the reflection and the transmission of the wave. When we have the wave that move pass through the different medium, we will find that there is a reflection and transmission of the wave at the boundary of the medium. To see what is the reflection and the transmission of the wave, let us first see the extreme example of the wave pass through the different medium. First, if we have a string and we make a paw to move along the string, and at one end of the string it attached to the wall, to the fixed wall. Okay, so it means that the point here is fixed. This end point is fixed. Okay, and once the paw approach the wall, we will have the reflection of the wave away from the wall. Now, from the experiment, we will have that the reflected paw will have we say that it's out of phase of the incident paw. It means that if the incident paw, the medium is moved upward like this, it's moved upward like this, the reflected paw will move downward like this. To explain this property, we can use the concept of the imaginary wave. What I mean is that when we look at the paw, for example, at this time, we can imagine that there is an imaginary paw move to the left like this. This imaginary paw is identical to the real paw that move on the string, except that it moves in a different direction. So you can see that since the real paw and the imaginary paw are identical, when it meet at this point, the motion of the medium will cancel, right? At this point, the motion of the medium will cancel between the real paw and the imaginary paw. The motion of at this point is cancelled. So it means that at this point, the medium will not move. The medium is not moved, which agree with our condition that we say that at this end the string is fixed to the wall. And we can see that to have these two waves cancel, it means that the phase of the incident wave and the imaginary wave will be pi, the phase difference, or 180-degree difference. So when this pole move up, the imaginary pole move down, and when the incident pole pass into the wall, the imaginary pole will move out of the wall. So at the end, the imaginary pole become a true pole, while the incident pole disappear, but we have this reflected pole instead with the phase 180-degree different from the incident pole. So we have the reflected pole that the medium move in the opposite direction to the incident pole. Now let us look at the other extreme, that is now the wave move along the string again, but it will hit the free end. This is the free end. For example, if you have a bar this and you connect the string at a ring here that can move freely along this bar or this rod. From experiment, we found that the reflected pole will have the same phase as the incident pole. It means that if the incident pole oscillate up, the reflected pole will oscillate up also, and this can be explained similar to the previous case. Now the spring can move freely here, so it means that when it reaches this rod and this ring, the ring will move up this. We can use the concept of the imaginary wave in this case, that we have the imaginary pole that move on the opposite direction to the real pole, and in this case, since this is a free end, the imaginary pole will move on a straight line that on the straight line on the string. Okay, so once the pole passes through the boundary, the imaginary pole will become a real pole, and it will have the same phase as the incident pole. Now let us discuss the situation that the pole pass through the medium with the different density. First, let us look at the pole that travel in the medium. It has a smaller linear density and then pass to the boundary, this boundary to the medium with heavier, have the larger linear density. We can see that this is similar to the case of the fixed boundary. In the case of the fixed boundary, we can imagine that the medium on the right is infinitely larger. I mean the linear density is infinitely larger than the string on the left. So the pulse cannot pass through that medium. Okay, if we look at this, and the wall, it can be assumed like a string that infinitely, the linear density is infinitely larger than the string on this side. But in this case, the string here is not infinitely, the density of the string here is not infinitely larger than the string here. So it means that some part of the pulse can pass through the string in this side. Since the string on the right here is heavier than the string on the left, what we expect is that the amplitude of the pulse that pass through the string on the right is smaller than the magnitude of the pulse of the incident pulse. Okay, because it's harder to move the medium on this side, so the amplitude should be smaller. So if we have the wave that pass through this boundary and then the amplitude is smaller, it means that we must have the imaginary pulse that pass through the boundary, and with the phase different, I mean the medium displays in the different direction as the incident pulse. Okay, so it means that at this point the total pulse will have the smaller amplitude like this, because if we cancel with the reflected pulse that move back to the left. Now let's consider the case that the pulse moves along the medium that has the larger linear density than on the right. Again, when the wave hit the boundary, there is a reflected wave and a transmitted wave. In this case, you can see that the boundary can be assumed as a free boundary. The free boundary is the extreme case, that is, we assume that the medium beyond this point has zero mass, so it can move freely without the inertia. But in the real situation, the density, the linear density of the string is not zero. So you can see that we must have the reflected wave to go together with the transmitted wave. If we combine these two waves, we should have the bigger the bigger size of the pulse. In this case, the reflected wave will oscillate with the same direction as the incident wave, and the transmitted wave will move away from the junction.